Langchain Postgres Chat Message Histories. Langchain Postgres Chat Message Histories is a tool that allows you to store and retrieve chat message histories in a PostgreSQL database. This tool enables you to keep track of conversations between users and an application, which can be useful for various purposes such as analyzing user behavior, providing context for future interactions, or debugging issues. Inputs. Chat messages. This refers to the actual text content of the conversations between users and the application. The messages can include questions, answers, commands, responses, and any other relevant information exchanged during the chat session. For example, a chat message could be "What is the weather in London today?" or "Please show me the latest news headlines." User ID. This is a unique identifier for each user interacting with the application. It allows the tool to distinguish between different users and track their individual chat histories. For example, a user ID could be a numerical value assigned to each user during registration or a unique email address used to identify them. Outputs. Chat message history. For a specific user, the tool's output is the complete history of chat messages. For a particular user, this history can be retrieved based on the user's ID, allowing you to access all the messages exchanged between the user and the application. For instance, if a user with user Idaho 1234 has had several conversations, the output would include all the messages exchanged during those conversations, providing a comprehensive record of their interaction. Steps. Connect to PostgreSQL database. The first step involves establishing a connection to the PostgreSQL database where the chat message histories will be stored. This requires providing the necessary database credentials, such as the host name, database name, username, and password. The tool uses the provided credentials to authenticate with the database and open a connection, allowing it to interact with the database and perform operations such as creating tables, inserting data, and retrieving information. Create a table to store chat message histories once connected to the database. The tool creates a dedicated table to store the chat message histories. This table will have columns to store information such as the user ID, the chat message itself, the timestamp of the message, and any other relevant details. The structure of the table is defined based on the specific requirements of the application and the data that needs to be stored. For example, the table could include columns for the user's name, the date and time of the message, and the context of the conversation. Insert chat messages into the table as chat messages are exchanged between users and the application. The tool inserts these messages into the previously created table. Each message is recorded with the corresponding user ID, the timestamp, and other relevant information. This process ensures that all chat messages are captured and stored in the database for future retrieval and analysis. For example, when a user asks "What is the weather in London today?" this message is inserted into the table along with the user's ID and the current timestamp. Retrieve chat messages from the table. Finally, when you need to access the chat message history for a specific user, the tool uses the user's ID to retrieve the relevant messages from the table. It performs a query on the table, filtering the data based on the specified user ID, and returns the corresponding chat messages. For example, if you want to retrieve the chat history for user Idaho 1234, the tool will search the table for all messages associated with this ID and return the complete conversation history for that user. Prerequisites. PostgreSQL database. The tool requires a PostgreSQL database to function. PostgreSQL is a powerful Open source object relational database system that is widely used for storing and managing data. It provides features such as asset properties, atomicity, consistency, isolation, durability, strong data integrity, and a robust query language. PostgreSQL 10 or later. The tool requires a specific version of PostgreSQL to ensure compatibility with its functionality. Version 10 or later is recommended to benefit from the latest features and security enhancements. Langchain library. The tool relies on the langchain library, a powerful framework for building and deploying language models. Langchain offers functionalities such as text embedding, chain building, and integration with external tools like databases. Langchain 0.0.219 or later. It is recommended to use Langchain version 0.0.219 or later to take advantage of the latest improvements and bug fixes. Fine-tune parameters. Database connection parameters. These parameters specify how the tool connects to the PostgreSQL database. They typically include the host name or IP address of the database server, the port number, the database name, the username, and the password. These parameters ensure that the tool can establish a secure and reliable connection to the database, allowing it to perform the necessary operations. For example, you might provide parameters like host localhost, port 5432, database chat history, user admin, and password my secret password. Table name. The table name is a user-defined identifier for the table that stores the chat message. Histories. It is used to refer to the specific table within the database. This name should be descriptive and reflect the purpose of the table. For example, chat messages or user conversations. Choosing a clear and concise table name helps in organizing the database and makes it easier to identify and access the relevant data. Challenges and fixes. Database connection errors. These errors occur when the tool cannot establish a connection to the PostgreSQL database. The most common reasons include incorrect database connection parameters, invalid credentials, or network connectivity issues. Check database connection parameters and credentials to resolve connection errors. Carefully review and verify the database connection parameters provided to the tool. Ensure that the host name, port number, database name, username, and password are correct and match the configuration of the PostgreSQL database. Also, confirm that the credentials are valid and have the necessary permissions to access the database. If necessary, check the network connection to ensure that the database server is reachable. Table creation errors. These errors arise when the tool encounters problems creating the dedicated table to store chat message histories. Common causes include insufficient permissions, conflicts with existing table names, or issues with the table schema. Check table schema and permissions to address table creation errors. Examine the table schema to ensure that it is valid and conforms to PostgreSQL syntax. Verify that the table name is unique and does not conflict with other existing tables in the database. Also, confirm that the user account associated with the database connection has sufficient permissions to create new tables. Data insertion errors. These errors occur when the tool cannot successfully insert chat messages into the table. Potential reasons include data type mismatches, violations of table constraints, or database performance issues. Check data types and constraints to fix data insertion errors. Review the data types defined for the table columns and ensure that the data being inserted matches those types. For example, if a column is defined as an integer, make sure you are not trying to insert text values. Additionally, examine the table constraints, such as primary keys, foreign keys, or unique constraints, to ensure that the data being inserted meets these requirements. Data retrieval errors. These errors happen when the tool cannot retrieve chat messages from the table. Common causes include incorrect query syntax, invalid table names, or issues with data filtering. Check query syntax and table name to resolve data retrieval errors. Double-check the query syntax used to retrieve the data. Ensure that the query is correctly formulated, includes the correct table name, and uses the appropriate filtering criteria to identify the desired messages. If necessary, verify that the table name used in the query is correct and matches the name of the table storing. The chat message histories. Langchain Postgres chat message histories summary. A description of a langchain tool that facilitates retrieving and storing chat history from a PostgreSQL database. Inputs. A list of chat messages. For example, this could be a series of user queries and chatbot responses within a conversational interface. The name of the database table storing chat history. For instance, chat history or conversation logs would be suitable table names. Outputs. The retrieved chat history. This would encompass the stored conversations, which could include user queries, bot responses, timestamps, and any other relevant information. Steps. Initialize a PostgreSQL database connection. This step establishes a connection to the database server. Using credentials and settings. Convert chat messages into a list of dictionaries. This step transforms the chat messages into a structured format, suitable for storage in a database. Each dictionary typically represents a single chat message and might include fields such as user, message, bot response, timestamp, and other relevant details. Store the chat message dictionaries into the PostgreSQL table. This step writes the transformed chat message data into the designated database table. Retrieve the chat history from the PostgreSQL table. This step reads the stored chat data from the table, potentially based on specific criteria like timestamps, user IDs, or other filters. Prerequisites. A PostgreSQL database. This refers to a PostgreSQL database server instance, which is required to store the chat history data. A PostgreSQL database connection string. This is a string containing all the information needed to connect to the PostgreSQL database. It usually includes the database server host, port, database name, username, and password. An example would be PostgreSQL name, password, host, port, database name. A PostgreSQL table to store chat history. This refers to a table in the PostgreSQL database dedicated to storing the chat messages. A schema for the PostgreSQL table. This defines the structure of the chat history table. It outlines the columns, e.g., user message, bot response, timestamp, and their data types, ensuring consistency and organization of the chat history data. Fine-tune parameters. Table name for chat history. This is the actual name given to the table used for storing chat data within the PostgreSQL database. Database connection string. This is the string used to connect to the PostgreSQL database, containing the necessary information about the server, database, and user credentials. Challenges and fixes. Handling large amounts of chat history. Chat applications can generate significant data. This can lead to performance issues if the database becomes too large. Implement pagination for retrieval. Pagination involves dividing the large amount of chat history into smaller chunks, retrieved one at a time. This prevents overloading the system and improves performance, especially when retrieving a long history. Maintaining data integrity. Ensuring data consistency and accuracy is crucial in any database application. Use appropriate data types and constraints. Selecting appropriate data types, e.g., text, timestamp for the columns in the table helps ensure the integrity of the data stored. Constraints, such as primary keys and foreign keys, enforce relationships between tables and maintain the consistency of the data, ensuring secure access. Protecting the chat history data from unauthorized access is essential. Use authentication and authorization. Authentication verifies the identity of users trying to access the database, while authorization defines which resources they can access. This ensures that only authorized users can access the chat history data. Langchain Postgres Chat Message Histories. Postgres Chat Message History. This component, Postgres Chat Message History, is designed to store the history of chat messages within a PostgreSQL database. This allows for efficient retrieval and analysis of chat interactions. Inputs: a list of chat messages, representing the conversational exchanges to be stored in the database. Each message would typically contain details such as the sender, the content of the message, and the time it was sent. Outputs: the primary output of this component is the successful storage of chat message history within a specified PostgreSQL database. This means that the chat messages are permanently saved and can be accessed later. Steps: the process starts with the instantiation of the Postgres Chat Message History class. This class encapsulates the functionality needed for interaction with the PostgreSQL database. Next, the component establishes a connection to the PostgreSQL database. This connection is facilitated by the provided database URL, which specifies the location and access credentials of the database server. Once the connection is established, the chat messages are inserted into the designated table within the database. This involves writing the message details, such as sender, content, and timestamp, into the appropriate columns of the table. Prerequisites: a PostgreSQL database must be installed and properly configured on the system. This includes setting up the database server, configuring its parameters, and ensuring it is running. The PostgreSQL client library is essential for the component to communicate with the database. This library provides the necessary functions for establishing connections, executing queries, and manipulating data. A dedicated table needs to be created within the PostgreSQL database for storing the chat message history. This table should have columns to accommodate the relevant message details, such as a unique message identifier message ID, the user who sent the message user ID, the content of the message content, and the time the message was sent timestamp. Fine-tune parameters. Database URL. This parameter specifies the URL of the PostgreSQL database, providing the necessary information for connecting to the server, including the host, port, database name, and authentication details. For example, a typical database URL might look like Postgres username, password, host, port, database name. Table name. The table name parameter defines the name of the table within the PostgreSQL database, where the chat message history will be stored. It is important to choose a descriptive name that reflects the purpose of the table, such as chat message history. Challenges and fixes. Connection issues can arise when trying to connect to the PostgreSQL database. Verify the database URL, ensuring that the host, port, database name, username, and password are correct and correspond to the actual database configuration. Make sure the PostgreSQL database server is running. If the server is not active, the component will be unable to connect. Ensure that the PostgreSQL client library is installed correctly and accessible to the component. The specified table might not be found. or it could be missing some of the required columns. Double-check that the table name provided in the table name parameter matches an existing table in the database. If the table does not exist, create it using SQL commands, defining the columns needed for storing the message details. If the table exists but lacks necessary columns, use SQL commands to add the missing columns to the table, ensuring they have the correct data types and constraints. LangChain Postgres Chat Message Histories. Postgres Chat Message History Summary. A tool for storing and retrieving chat message histories in a Postgres database. This tool allows you to persist the conversation history between a user and a language model within a Postgres database. It enables you to analyze and retrieve past conversations easily. For instance, if you are building a chatbot, you can utilize this tool to store the interactions of each user for future analysis or to provide context in future conversations. Inputs: a list of chat messages. The list comprises individual chat messages that represent the complete conversation history. Each chat message may contain the message text, sender, timestamp, and other relevant information. You could leverage this tool to store various conversational interactions like customer support, inquiries, user queries, or general conversations. Outputs: a Postgres chat message history object. This object is a representation of the stored conversation history in the database. It contains information like the conversation ID, timestamps, message content, and other relevant data. This object can be used to access and manage the stored conversation history. Steps: initialize the Postgres chat message history object. Create an instance of the Postgres chat message history object by providing necessary configuration parameters, like the database connection details and the table name to be used. Connect to the Postgres database. Establish a connection to the Postgres database using the provided database connection parameters. The parameters include the database name, host, port, user, and password. The connection establishes a communication link between your code and the database. Store chat messages in the database. Insert the list of chat messages into the specified table within the Postgres database. This step involves formatting the messages according to the table schema and using appropriate database queries to insert the data. Prerequisites: Postgres database. To utilize this tool, you need a Postgres database. Postgres is a powerful and popular open-source relational database management system, known for its reliability, performance, and features. You need to have the Postgres database installed and configured on your system. Postgres database name, Postgres database host, Postgres database port, Postgres database user, Postgres database password. These are the credentials that allow you to connect to and access the Postgres database. The database name identifies the specific database you wish to connect to. The host specifies the server where the database is located. The port is the communication channel for the connection. The user is the account with access privileges. And the password is the authentication key. LangChain library. The LangChain library is essential for interacting with language models and building various applications using them. This library provides tools and functions for managing chains of thoughts and actions, making it easier to build complex applications with language models. LangChain version. The LangChain version specifies the specific release you are using. It is important to ensure that the LangChain library version matches the compatible version of other libraries and tools in your project. Fine-tune parameters. Database connection parameters. These parameters allow you to connect to and access the Postgres database. They include the database name, host, port, user, and password. Table name. The table name is the identifier of the table within the Postgres database where you will store the chat message histories. It is recommended to choose a descriptive table name to make it easier to manage your data. Challenges and fixes. Error connecting to the database. If you encounter an error connecting to the database, you should first check the database connection parameters. Ensure that the database name, host, port, user, and password are correct and match the configuration of the Postgres database. Check database connection parameters. Check Postgres database status. Additionally, you should verify the status of the Postgres database. Check if the database server is running and accessible. If the server is not running or is experiencing issues, restart it or troubleshoot the server-side problems. Error storing chat messages. This error could occur if there are issues with the table schema or database permissions. Check table schema. Check database permissions. To troubleshoot this issue, check the table schema and ensure it matches the format of the chat messages you are trying to store. Also, verify that your user account has the necessary permissions to write data to the specified table within the database. Summary of langchain Postgres checkpoint pickle checkpoint serializer. This component of langchain allows you to store checkpoints, which are essentially snapshots of the state of your language model, in a PostgreSQL database using the Python pickle library. Inputs. The input to this component is the actual checkpoint data. Checkpoints capture the current state of your language model, including its parameters, vocabulary, and other essential information. Outputs. The output of this component is the successfully saved checkpoints within your PostgreSQL database. These stored checkpoints can then be used to restore the state of your language model at a later time, allowing you to resume training or use the model from a previous point. Steps. The process begins by using the pickle library to serialize or convert the checkpoint data into a byte stream. This conversion makes the checkpoint data suitable for storage in the database. The next step is to store the pickled checkpoint data in a designated table within your PostgreSQL database. This table is specifically designed to hold these serialized checkpoints. Prerequisites. This component requires a PostgreSQL database to be already installed and configured on your system. PostgreSQL is a popular and robust relational database management system. The PsychoPG2 package is a Python library that provides an interface to interact with PostgreSQL databases. You'll need this package installed in your Python environment to connect and manage data within your database. A dedicated table needs to be created in your PostgreSQL database to store the serialized checkpoints. This table should have a schema that is suitable for storing the pickled data. The schema typically includes columns to store the checkpoint identifier, the serialized data itself, and possibly timestamps for tracking when checkpoints were created or last modified. Fine-tune parameters. The table name parameter specifies the name of the PostgreSQL table where checkpoints will be stored. This name should be descriptive and reflect the purpose of the table. The column name parameter specifies the name of the column within the designated table where the serialized checkpoint data will be saved. It's best to choose a name that clearly indicates the content of this column. Challenges and fixes. Pickling large checkpoints can lead to performance issues, as the process of converting the data to a byte stream can take a significant amount of time. To address this, consider using a more efficient serialization method that is optimized for handling large data, such as Apache Avro or Protocol buffers. These methods typically achieve faster serialization and deserialization speeds compared to Pickle. PostgreSQL can experience slow write speeds when dealing with large amounts of data, especially when writing checkpoints that are large in size. One approach to mitigate this is to explore using a faster database system, such as Redis or MongoDB, which are known for their performance in handling large data volumes. If you prefer to stay with PostgreSQL, consider optimizing its settings, such as increasing the buffer size or adjusting the write-ahead log settings to enhance write performance. Langchain Pinecone Vector Stores. Pinecone. A langchain Pinecone vector store is a system that enables the embedding and retrieval of information from large datasets. It functions by converting text into numerical representations, known as embeddings, and storing these embeddings in a vector database. This allows for efficient search and retrieval of relevant information based on similarity between embeddings. Inputs. Text data: raw text that needs to be processed and converted into embeddings. For example, articles, documents, or blog posts. Embeddings: numerical representations of text data that capture the meaning and relationships between words. These are generated using embedding models like sentence transformers or OpenAI's text embedding GADA 002 model. For example, an embedding for the text "the quick brown fox jumps over the lazy dog" would be a vector of numbers that represents the meaning of the sentence. Outputs. Vector store: a database that stores and organizes embeddings. Pinecone is a popular vector database that allows for efficient storage and retrieval of embeddings. This serves as the foundation for information retrieval. Similar embeddings: when a query is provided, the system retrieves embeddings that are similar to the query's embedding. These similar embeddings represent text data that is relevant to the query. This enables search and retrieval of information based on semantic similarity. Steps. Create a vector store. Initializes the Pinecone class, connecting to the Pinecone vector database and specifying the index where the embeddings will be stored. This step establishes the foundation for storing and retrieving embeddings. Add data to the vector store. Provides text data to the vector store, which then converts the text into embeddings using an embedding model and stores the embeddings in the Pinecone index. This process populates the database with meaningful numerical representations of the text data. Retrieve similar data. When a query is given, the system converts it into an embedding using the same embedding model. It then uses this query embedding to search for similar embeddings within the Pinecone index. This step retrieves the embeddings that are closest in meaning to the query, effectively identifying relevant information from the dataset. Prerequisites. Pinecone account and application programming interface API key. This is required to access and interact with the Pinecone vector database. You will need to create an account and obtain an API key from the Pinecone website. https://www.pinecone.io. Pinecone index: a dedicated storage space within the Pinecone vector database where embeddings are stored. This index acts as a container for the embeddings, enabling efficient retrieval and organization. Fine-tune parameters. Dimension of the embeddings: the number of features or dimensions that represent each embedding. This value is determined by the embedding model used and influences the complexity and accuracy of the embeddings. For example, a larger dimension allows for more nuanced representations of text data. Metric for similarity calculations: the method used to calculate the similarity between embeddings. This metric determines how the system measures the closeness of two embeddings. Examples include cosine similarity, Euclidean distance, and dot product. The choice of metric depends on the specific application and the characteristics of the embeddings. Challenges and fixes. Challenge 1. Slow retrieval times due to large dataset size when dealing with vast amounts of data. Retrieving relevant information can become slow due to the need to search through a large number of embeddings. This can impact the user experience, making the retrieval process less responsive. Fixes to challenge 1. Use top K parameter. This parameter limits the number of retrieved embeddings to only the most relevant ones. This reduces the search space and significantly improves retrieval speed, especially when dealing with large datasets. It prioritizes the most similar embeddings, ensuring efficient and timely results. Challenge 2. Inaccurate search results due to poor embeddings quality. The accuracy of information retrieval heavily depends on the quality of the embeddings. If the embeddings do not accurately represent the meaning of the text data, the search results may be inaccurate or irrelevant. Fixes to challenge 2. Use a more powerful embedding model. Selecting a more powerful embedding model, like sentence transformers with a larger model or a more specialized model tailored to the specific domain, can significantly improve the quality of the embeddings. These models often have more parameters and are trained on larger datasets, leading to more accurate and nuanced representations of text data. Fine-tune the existing model. Fine-tuning an existing embedding model on a domain-specific dataset can improve its ability to capture the nuances of the text data within that domain. This customization can enhance the quality of the embeddings, leading to more accurate search results. This is particularly beneficial when the dataset has a specialized vocabulary or unique characteristics. LangChain PostgreSQL Vector Stores. A guide to efficient embedding storage and retrieval. A vector store built on top of PostgreSQL database for efficient storage and retrieval of embeddings. PostgreSQL is a powerful and widely used open-source relational database management system. It provides robust features such as transactions, concurrency control, and data integrity, making it suitable for storing and retrieving large volumes of embeddings. LangChain provides a wrapper for PostgreSQL to facilitate embedding storage and retrieval in a user-friendly manner. This allows developers to leverage the capabilities of PostgreSQL for efficient vector search and retrieval without needing to manage the underlying database infrastructure. Inputs. Text data refers to the raw text content that needs to be converted into an embedding vector. These can be documents, articles, product descriptions, or any other type of text. For example, a user manual, an article on a scientific subject, a product description, or a social media post can all be considered text data for this context. Embeddings are numerical representations of text data that capture its meaning and semantic relationships. They are typically generated using machine learning models, such as sentence transformers, OpenAI, or other embedding models. Embeddings can be used to measure the similarity between pieces of text, which allows for efficient search and retrieval. For example, an embedding for the phrase "the quick brown fox jumps over the lazy dog" will be similar to an embedding for the phrase "a fast brown fox jumps over the tired dog." Outputs. Similar text documents are documents retrieved from the PostgreSQL database based on their similarity to a given query embedding. The similarity search is typically performed using a distance metric, such as cosine similarity or Euclidean distance. This allows you to find documents that are semantically related to the query, even if they do not share the same words. For example, if a user searches for documents similar to a query embedding representing the phrase "artificial Intelligence. The vector store will return documents containing phrases like machine learning, deep learning, or neural networks which are semantically related to the original query, even though these phrases do not contain the exact words. Embeddings, as described before, are numerical representations of text data used to measure semantic similarity. Steps. 1. Create an embedding of the text data. This step involves converting the raw text data into numerical representations using an embedding model. This model will analyze the text and produce a vector that captures its meaning and semantic relationships. 2. Store the embeddings and their corresponding text in a PostgreSQL table. The embeddings are stored as numerical vectors in the database, along with their associated text data. This allows for efficient retrieval of similar documents based on embedding similarity. 3. Use similarity search to retrieve relevant documents based on embeddings. Given a query embedding, the vector store performs a similarity search in the PostgreSQL table to find embeddings that are closest to the query embedding. The distance metric used for similarity search can be configured based on the specific requirements of the application. For example, cosine similarity is often used for finding documents with similar meaning, while Euclidean distance might be preferred for finding documents with similar word counts. Prerequisites. PostgreSQL database is a powerful and widely used open-source relational database management system. It provides robust features such as transactions, concurrency control, and data integrity, making it suitable for storing and retrieving large volumes of embeddings. You can use a local PostgreSQL installation or a cloud-based PostgreSQL service provided by cloud providers such as Amazon Web Services (AWS), Google Cloud Platform (GCP), or Microsoft Azure. The Embeddings Library is a software library that provides functions for generating embeddings from text data. Popular embedding libraries include sentence transformers, OpenAI, and others. These libraries offer pre-trained models that can be used to generate embeddings for various tasks, such as text classification, question answering, and semantic search. Fine-tune parameters. Distance metric refers to the mathematical function used to measure the similarity or dissimilarity between two embedding vectors. Common distance metrics include cosine similarity, Euclidean distance, and Manhattan distance. The choice of distance metric depends on the specific application requirements and the type of embedding model used. For example, cosine similarity is often used for finding documents with similar meaning, while Euclidean distance might be preferred for finding documents with similar word counts. Index type refers to the data structure used to store and search the embedding vectors. Different index types provide different trade-offs between search speed and storage space. Common index types include KD trees, ball trees, and HNSW hierarchical navigable small world. The choice of index type depends on the size and dimensionality of the embedding vectors, as well as the expected search frequency and performance requirements. Challenges and fixes. Slow query performance can occur when searching for similar documents in a large database of embeddings. This can be caused by factors such as inefficient database schema, lack of indexing, or inadequate hardware. To address this challenge, you can optimize the database schema by creating appropriate indexes and using appropriate data types for storing embeddings. Additionally, you can consider using a dedicated search engine, such as Elasticsearch, for faster search performance. Memory issues can occur when loading large datasets of embeddings into memory. To address this challenge, you can chunk the text data into smaller segments and process each chunk separately. Alternatively, you can use streaming methods to process the data without loading the entire dataset into memory. Scalability concerns arise when dealing with massive datasets of embeddings. To address these concerns, you can use a distributed database system, such as a cluster of PostgreSQL servers, to distribute the data and improve query performance. Additionally, you can employ caching techniques to store frequently accessed embeddings in memory for faster retrieval. Langchain PostgreSQL vector stores. A concise overview expressed with elaborations. Storing and retrieving vector embeddings in a PostgreSQL database. This technique allows for efficient search and retrieval of similar text based on semantic meaning, rather than just exact keyword matching. Inputs. Text data to be embedded. This includes the text you want to analyze and search for similar content. For example, a collection of news articles, product descriptions, or customer reviews. Pre-trained embedding model. This is a machine learning model trained to map text into numerical vectors that represent its meaning. Popular models include sentence transformers, OpenAI's text embedding ADA002, and others. Outputs. Vector embeddings stored in PostgreSQL. These are the numerical representations of your text, stored in a PostgreSQL table for efficient querying and retrieval. Similar text based on vector similarity search. This output is a list of text items ranked by their similarity to a query based on their vector representations. The closer the vectors, the more semantically similar the text. Steps. Create a PostgreSQL table with columns for text and vector embedding. This table structure is specifically designed to store the original text and its corresponding vector representation. Use a langchain vector store to embed text and store embeddings in the table. The langchain vector store API provides an interface for interacting with the database and pay. Embedding model. It embeds your input text into vectors and stores them in the PostgreSQL table. Perform similarity search using the vector store. Once the text data and embeddings are stored in the PostgreSQL table, the langchain vector store allows you to perform similarity searches. You provide a query text and the vector store finds the most similar text entries in your database by comparing vectors. Prerequisites. PostgreSQL database. A PostgreSQL database is necessary to store the vector embeddings. A database instance. This refers to a running PostgreSQL database server where you can create and manage your database. LangChain library. The LangChain library is a powerful tool for building LLM applications. Install with pip install langchain. This command downloads and installs the langchain library and its dependencies. Fine-tune parameters. Embedding model type. The choice of embedding model can influence the quality of your similarity search results. Different models have varying strengths and weaknesses based on factors like training data and model architecture. Similarity search algorithm. The method used to measure similarity between vectors can also impact results. Common algorithms include cosine similarity, Euclidean distance, and dot product. Challenges and fixes. Slow query performance. Querying large vector datasets can be computationally expensive. Optimize database indexing and query execution plans. Creating indexes on the vector columns and tuning your query plans can significantly improve performance. Scalability limitations. As your dataset grows, traditional relational databases might face scalability challenges when handling large vector datasets. Use a dedicated vector database or distributed PostgreSQL setup. Specialized vector databases like Pinecone, Milvus, or FIS are designed to handle massive vector datasets efficiently. Distributed PostgreSQL setups can also help scale your database to handle large volumes of data. Langchain OpenAI LLMS Azure OpenAI Summary. This describes the Azure OpenAI service integration with LangChain. It details how to use the Azure OpenAI service within the LangChain framework to leverage powerful language models for various tasks. Inputs. Text input for the Azure OpenAI model. This is the text you want the model to process. For example, you can provide a question, a prompt, or a piece of text you want the model to summarize. Azure OpenAI deployment name. This refers to the specific Azure OpenAI model deployment you have configured in your Azure account. Each deployment represents a specific model with its own configuration and settings. Outputs. Response from the Azure OpenAI model. This is the output generated by the Azure OpenAI model based on the input text and the chosen deployment. It can be a response to a question, a summary of the input text, or any other output format defined by the model. Steps. Instantiate the Azure OpenAI class with your deployment name and application programming interface. Key. This involves creating an instance of the Azure OpenAI class, providing your deployment name, and your API key. The API key is used for authentication and authorization to access the Azure OpenAI service. Call the predict method to send text to the model. Once the Azure OpenAI class is instantiated, you use its predict method to send the input text to the model. This method takes the input text as an argument and sends it to the Azure OpenAI service for processing. Prerequisites. Azure OpenAI resource. To use the Azure OpenAI service, you need an Azure OpenAI resource in your Azure account. This resource provides access to the Azure OpenAI models and their functionalities. You can create an Azure OpenAI resource through the Azure portal. Azure OpenAI resource details. The Azure OpenAI resource details include information about your Azure subscription, resource group, deployment name, and other settings related to your Azure OpenAI resource. Azure OpenAI Application Programming Interface Key. The Azure OpenAI Application Programming Interface Key is used for authenticating and authorizing access to your Azure OpenAI resource. It acts as a secret key for securing your access to the service. Azure OpenAI Application Programming Interface Key details. This key should be kept securely and used only for authorized access to your Azure OpenAI resource. It's essential to protect your API key to prevent unauthorized access to your account and resources. Fine-tune parameters. Temperature. This parameter controls the randomness of the model's output. Higher temperature values result in more creative and unpredictable outputs, while lower values lead to more predictable and deterministic outputs. Max tokens. This parameter specifies the maximum number of tokens that the model is allowed to generate in its response. It helps limit the length of the output and prevent excessively long responses. Challenges and fixes. Application Programming Interface Key issues. Issues with your application programming interface key can occur if the key is invalid, expired, or has incorrect permissions. Troubleshooting steps. Troubleshooting steps for application programming interface key issues include verifying the key's validity, ensuring it is correctly entered, checking for expiration, and verifying access permissions. Deployment name issues. These issues occur when the specified deployment name is incorrect or does not exist. Troubleshooting steps. Troubleshooting steps for deployment name issues involve checking for typos in the deployment name, verifying the deployment exists in your Azure OpenAI resource, and ensuring the deployment name is correctly formatted.